This lesson deals with supplemental problem 5.10. You can find this problem in the course ebook in the Chapter 5 supplemental problem starting on page 13. Given this one inductor circuit with a switch that opens at time t equals 0, could you find the current I1 of t, I sub L of t, and V sub L of t for all time? Using our 6-step algorithm, our first step is to formulate the equations. I1, I sub L, and V sub L are first-order differential equation solutions of sum a plus b times e to the minus quantity t minus t0 over tau, but t0 is equal to 0. Since we have three different quantities, let's call the first one with a 1 subscript, the second one with a 2 subscript, and the third one with a 3 subscript. Step 2 is to find the pre-switching conditions of our variables I1, I sub L, and V sub L at time t equals 0 minus. Now whether we're solving for this or not, we have to solve for the inductor current, because that's the one thing that can't jump instantaneously. Prior to the switch opening, the switch has been closed for a long time, and an inductor looks like a short circuit if it's in a DC circuit for a long time. Let's find the voltage across this resistor with this short circuit. I've got 12K in parallel with 6K. That forms a voltage divider with the 3K resistor. 6K in parallel with 12K, divided by that plus 3K times the 42 volts that's here. That turns out to be 24 volts. If this is 24 volts, then this is also 24 volts. The current I1 then is 24 volts divided by 6K, and the current in the 12K resistor, which is the inductor current, is 24 volts divided by 12K. And that's 4 milliamps and 2 milliamps. Step 3 is to find the initial conditions. At time t equals 0, the switch opens up. The current in the inductance cannot change instantaneously, so it was 2 milliamps. Prior to the switch changing state, it must still be equal to that value. That's going to be A2 plus B2 times e to the 0, which is equal to 1. Just A2 plus B2. The current that's flowing in this inductor flows back this way because of the open circuit. Nothing's going back this way, so it's going to flow around this way. The current in the inductor is the negative of the current I1. I1 of 0 plus is a minus 2 milliamps, and that's going to be A1 plus B1 times e to the 0, or just A1 plus B1. The voltage across the inductor is going to be equal to this drop plus this drop. In other words, the rise in voltage equals this drop plus this drop. Current I1 is flowing in here, flowing through here. I1 of 0 plus times 12K plus I1 of 0 plus times 6K would equal the inductor voltage. Pull out the I1 of 0 plus, but I1 of 0 plus is minus 2 milliamps. Multiply that by 18K, get a minus 36 volts. That's going to be A3 plus B3 times e to the minus 0, or A3 plus B3. Our next step is to find the final conditions of I1, I sub L, and V sub L as t approaches infinity. When an inductor is in a DC circuit for a long time, it looks like a short circuit. Short this, and the voltage across the inductor then would be equal to 0. That's going to be equal to A3 plus B3 times e to the minus infinity, or just A3. Now the current in the inductor flows around here because of the open circuit. No current is coming here or goes this way. This current just circulates around here, so I get a drop across here and a drop across here. Well, I sub L times 6K, I sub L times 12K, drop in voltage, and then another drop in voltage. I can put that drop on the other side of the equation as a minus 0. I'm going to add up two numbers with I sub L in it, but it has to sum to 0. The only number that works is if I sub L is 0. And that's going to be equal to our A2 plus B2 times e to the minus infinity, or just A2. And lastly, the current I1 is in the opposite direction of I sub L, and therefore it's a negative of it, but it's equal to 0, so it's also equal to 0, and that's going to be equal to A1 plus B1 times e to the minus infinity, or just A1. Step 5 is to find the Thevenin resistance. We'll set all the independent sources equal to 0, but the switch is open for t greater than 0. It doesn't really affect us. Looking back in here, what I see is 12K. This is in series with an open circuit, so this is just simply equal to 3K plus infinity. Looking in these terminals, I see 12K, 6K back to here, so total of 18K. My time constant is L over R Thevenin. L was 2 millihenries, and so that gives me 111 nanoseconds. Step 6 is to put it all together. A1 plus B1 was minus 2 milliamps. A1 was 0, so B1 is equal to minus 2 milliamps. I1 is equal to A1 plus B1 e to the minus t over tau. So minus 2 milli e to the minus t over 111 nanoseconds. This was true for t greater than 0. For t less than 0, we found that it was 4 milliamps. Now, do we have the equality? No, this is the current in a resistor, and if we just check it, when t is equal to 0, we wind up getting a minus 2 milli times 1, and that's not going to equal to 4 milliamps. We have a discontinuity at t equals 0. Let's sketch this. For t less than 0, we have 4 milliamps. When t is equal to 0, we have minus 2 milliamps. As t approaches infinity, or really 5 time constants, this term will drop out, get back to 0. Draw an exponential curve in 5 time constants, which would be 555 nanoseconds, that we basically go back to 0. For I sub L, we have A2 plus B2 is 2 milli. A2 was 0, so B2 is equal to 2 milli. I sub L is 2 milli times e to the minus t over tau. This is true for t greater than or equal to 0 because the current in an inductance cannot change instantaneously. And we found that it was equal to 2 milliamps for t less than 0. If you let t equal 0, you get 2 milli times e to the 0, which is 1, so you just get 2 milli. Sketch that. T less than 0, we have 2 milli. We cross through 0, we're still 2 milli, and then eventually in 5 time constants, this term will drop out, basically be 0. For V sub L, we have A3 plus B3 is minus 36. A3 was 0, so B3 is equal to minus 36. We have A3 plus B3 e to the minus t over tau, so 0 minus 36 e to the minus t over 111 nanoseconds. So it's true for t greater than 0. This is the voltage across the inductance, and it can change instantaneously, but let's just check it. T less than 0 is equal to 0 volts. T is equal to 0, plus we get a minus 36 times 1. There's a discontinuity. For t less than 0, we have 0. When t is equal to 0 plus, we drop down to minus 36, and then this term will die out in 5 time constants, so I'll go back to 0. And this is supplemental problem 510.